The invention of the light bulb is often considered one of the most pivotal points in the technological history of humankind. Light bulbs have enabled us to do so much more than candles or fuel-based lamps ever could have. Light bulbs help direct us. They protect us from harm by warning us, and they convey information. Not to mention how we're able to live fuller, more meaningful, more active lives at night. When we think about the invention of the light bulb, most people think of Thomas Edison, who's often associated with inventing them. Or if you're a Nikola Tesla fan, maybe you think that Tesla invented them and Edison simply stole the work, as he was prone to do. But here's the thing, neither of them really did. At least not in the ways that we typically think of inventions. We often think of inventions as that sort of, well, light bulb moment. We like to think of inventions as a sudden epiphany, a spark of ingenuity that comes out of nowhere. But it really isn't. Running an electrical current through a filament to generate light had been done a long time before Edison or Tesla ever started their work. In fact, inventing had started nearly 80 years before Edison filed his patent, and dozens of inventors at the time were producing light bulbs to varying degrees of success. The invention of the light bulb is actually built on multiple innovations. From the harnessing of electricity, to the discovery of using various materials as filaments, to the process to create clear glass, blow it into a bulb and pull a vacuum on it, or insert gas within that bulb. None of these individual innovations were discovered by any of the inventors working on creating light bulbs. Innovation isn't the process of building something entirely unique and different from anything that's existed before. Most often, it's the process of combining existing things in just the right combination to meet a need at just the right time. Author Steven Johnson calls this the adjacent possible. It's a term that he's borrowed from the biologist Stuart Kauffman. In evolutionary biology, each successful mutation of a species unlocks the possibility for more mutations that were not originally possible. Fish needed to evolve to have bones in their fins. And it was only when that happened that it became possible for them to develop limbs. And that made more mutations possible, which eventually allowed them to walk out of the water and begin life on land. Steven Johnson applies this same concept to innovation. Past innovations unlock the potential for future innovations. New combinations of innovations open up the possibility of even more new combinations. He describes it this way. Think of it as a house that magically expands with each door you open. You begin in a room with 4 doors, each leading to a new room that you haven't visited yet. Once you open one of these doors and stroll into that room, 3 new doors appear, each leading to a brand new room that you couldn't have reached from your original starting point. Keep opening new doors, and eventually, you'll have built a palace. But innovation is also fraught with failure. According to work published by Harvard Business School, over 95% of product innovations fail. So while some doors lead to innovation, most doors lead to failure. We're all trying to innovate. That's what technology is all about. And we've all experienced failure in the forms of incidents and downtime and outages. As our systems and applications become increasingly more complex, it's opened us up to even more failure. In the same way that innovations unlock the potential for even further innovation, small failures, minute anomalies, or performance degradations can build into major incidents. And this is why we say that there is never a single root cause, but many contributing factors. Stephen Johnson notes that sometimes the adjacent possibilities of innovation are practically inevitable. Advances in glass manufacturing in the 13th century led to the creation of lenses, which allowed us to bend light. That quickly led to the invention of reading glasses, lenses for your face. It doesn't take a stroke of genius to imagine simply increasing the magnification beyond reading small text to create the microscope for viewing even smaller details. But if some adjacent possibilities are more natural, more inevitable than others when it comes to innovation, maybe it applies as well to failure. Maybe you've encountered this. You run a retrospective on your incident, and there's one big contributing cause. Something that you never imagined would, or even could, have happened. And then you notice all the small contributing factors that enabled it, or allowed it, or perhaps even helped it along. So if we can be intentional about innovation, how can we explore the adjacent possibilities of failure in order to be more intentional about reliability? If you're working in technology, you are a smart person. You're intelligent, and you're hired for the knowledge you have and how you can apply that knowledge to new situations to solve new problems. When we talk about our complex systems, we often talk about three categories of knowledge. There are known knowns, things that you know that you know. You know how to write shell scripts, and you know that you know how to do that. You know that you know how to configure servers, and you've probably done that before. And of course, you know that buffalo wings were created right there in Buffalo, New York. There are also known unknowns. There are things that you know that you do not know. I'm sure you're aware that there are complex international trade policies that apply to imported chicken meat. But you also know that you don't know all the details of those trade policies. Not that you should, because nobody wants to eat imported frozen chicken wings. Similarly, you probably know that monitoring tools, for example Prometheus, support remote endpoints for long-term storage of metrics. But you probably know that you don't know the entire list of supported endpoints for Prometheus, and which ones are read-write versus write-only, and how to configure all of them. These are known unknowns. But one reason you're working in tech is that you're good at finding the answers to these unknowns and learning new solutions. Lastly, there are unknown unknowns. Things that are so foreign to you that you haven't considered them and haven't the faintest idea as to what you don't know. Is there a secret alien technology being hidden in Area 51? You don't know. But if there is, you wouldn't know where to start to list all of the things that you didn't know about that alien technology. When it comes to our own human technologies, major incidents are our unknown unknowns. We don't know when or where our next incidents are going to occur. And since they're unknown, we don't know what we don't know about them. Our future incidents are full of unknown unknowns. And here's where I think that we can be intentional about reliability and use the adjacent possible of failure to our advantage. You see, what makes you really valuable as an engineer is your ability to turn known unknowns into known knowns. This power also has the potential to turn unknown unknowns into known unknowns, to make us aware of the things we don't yet know. And when it comes to exploring failure and the adjacent possible, this is where I think that chaos engineering is a practice that can radically change the work that you do and the reliability of your systems and applications. Chaos engineering as an informal practice has been around for longer than technology. Humans are bold and curious, and we've been experimenting in production since the beginning of our time. The first human who saw a rotted cabbage, or the slippery, gelatinous inside of a rock-like thing in the water, or some fruit juice that started to smell a bit funky. And they thought, how bad could this be? And went on to discover sauerkraut and oysters and alcohol. Chaos engineering as a formal practice has also been around for quite a while. The folks at Netflix coined the term nearly 10 years ago, and various forms of chaos engineering existed well before that at companies like Amazon and Google. I like to define chaos engineering as scientific experimentation on our systems to improve our understanding of how they work and how they fail so that we can make them better. Our applications are only as good as the engineers that build them. So in order for you to build better systems, you need to become more knowledgeable. You need to convert known unknowns into known knowns through exploration, experimentation, and learning. Chaos engineering follows 5 steps that form the scientific process. The first is to observe your systems, to establish a baseline. How do your systems and applications behave under normal circumstances? Second, create a hypothesis. Given what you know about your systems, how do you think they'll behave in reaction to stress or failure? It's also important to consider your larger system as a whole. What will this stress or failure look like in your monitoring and observability tools? Will it trigger an alert? And if so, is there documentation to adequately respond and resolve the issue? Third, inject the failure and collect data. As you do this, it's important to keep 3 things in mind. The blast radius is how large of an impact your experiment will make. You want to make the smallest impact possible while still deriving good data. In many science experiments, there's a sample size. You don't need to subject the entire population to an experiment, but you need a large enough sample size to ensure accurate data. The same can be applied to your blast radius. Don't impact all of your services, clusters, or nodes, just enough to get good data. The magnitude is the severity of the failure or stress. Similar to the blast radius, we want to start with a small magnitude, just enough to get good data. Abort conditions are our guardrails. They're the boundary that we set to ensure that experiments don't have a negative effect on our customers or our colleagues. What are the conditions that would cause you to halt an experiment? Maybe it's a key metric that's important to your business, or a service level objective, or agreement. The fourth step in the process is to analyze the data. If it matched your hypothesis, that's fantastic. It means you've got a good understanding of your systems. If it didn't match your hypothesis, it's a good opportunity to determine if your understanding of the system needs to be updated, or if the system needs to be improved to match your expectations. As you analyze the data, this is where you need to consider the adjacent possibilities of failure. Given the failure you've injected and your system's response, what else could go wrong? From a technical perspective, are there contributing factors that would create a catastrophe? From a process perspective, where are you making assumptions in knowledge? Is there documentation? Or are there guardrails in place to minimize human factors leading to incidents? The fifth step of the process is to iterate. Address the action items that were raised in your experiment and repeat the process to validate your work and explore new areas. Early experiments will help you deepen your understanding, and iterating will allow you to keep pushing your boundaries, to explore what you don't know, and uncover unknown unknowns. And don't forget to share what you've learned, so others can benefit from your work. So where do you start? A basic restart test is an easy chaos engineering experiment to begin with. If you shut down a service, whether it's by killing a process, shutting down a VM, or deleting a pod, does it restart? This is a fundamental requirement for nearly every service. So you need to confirm that they restart automatically. And in doing this, turn known unknowns into known knowns. As you do that, consider what would prevent that service from restarting. What could the contributing factors look like? The more of these adjacent possibilities you can come up with, the more you'll uncover unknown unknowns and turn them into known unknowns. This is the process of stepping through another door into the adjacent possible and discovering more doors that you can explore. Keep opening new doors, and eventually you'll have more known knowns than unknown unknowns. And that's how you build reliability in a complex world.